Uh, Hello everyone. Today again we'll be seeing about the next topics of VLSI. We are in the previous class we have studied about what is meant by VLSI and why we are using VLSI and how the particular VLSI technology has evolved and what are the other technologies apart from VLSI we have even seen in the previous class. And we have even gone through the advantages and disadvantages of the VLSI and also to which areas the VLSI has stretched its arms. Even this part also we have completed in the previous class. So now today we will be studying about a concept called what are the different types of VLSI, how the VLSI design has been divided into how many types and depending upon different factors, and what is the main core device which thrives the VLSI technology, and again we'll see different kinds of fabrication techniques. So this will be the outline of the today's class. So okay, welcome to this class of course of VLSI. So VLSI design. VLSI design depending upon signals. VLSI design depending upon signals. It is divided into two. Basically, it is divided into three different types. The first kind of VLSI is called analog VLSI design. And second one is called as a digital VLSI design. And third one is called as a mixed signal VLSI design. So these are basically three different types of VLSI designs depending upon the signals, different kinds of signals. In analog VLSI design, mostly we'll be using analog kind of signals. In digital, we'll be using the zeros and ones, that's the digital signals. In mixed, both it will be a combination of both analog and digital signals. So these are the three different types of VLSI designs depending upon different types of signals here. Then next, the same VLSI design is also being classified into two different types depending upon the manufacturing of any of the IC. Depending upon manufacturing of IC, this VLSI design is classified into two different types. The first type is called as a front-end design, front-end VLSI design, front-end VLSI design, and the second one is called as a back-end VLSI design, back-end VLSI design. So what is this front-end and what is meant by back-end? So let us see now. Front-end means here, this particular part, front-end VLSI design, is basically regarding the designing and testing of the VLSI circuits. It's basically regarding the designing of the VLSI circuit and the designing of the, testing of the VLSI circuit. So now here, for the front-end design, mostly we'll be using the scripting languages. The scripting or the programming languages are being used. And in VLSI, there are nearly like 4 to 5 different kinds of scripting languages. Among these 4 to 5, most important languages are first one, vhdl, second one, verilog, and third one, system verilog. And for the testing, we'll be using like RTL logic. So these are the 4 different kinds of programming languages which have been used in VLSI. Which is mainly related with the front-end designing. For the front-end design means mostly you'll be working with the coding part, where you'll be writing the codes for different circuits like adders, counters, how they're working, and for subtractors, marks, multiplexers, and decoders, encoders, and all those things. For different modules, you'll be writing the programs, and that programming part is known as a front-end design. If anyone is interested in programming, they can choose the area called front-end VLSI design in order to become front-end engineers, front-end VLSI engineers. And the second part, coming to the second part, there is back-end VLSI design. This back-end VLSI design is mainly regarding the physical design and also layout designing of a particular circuit. It's mainly related with the physical design, how the particular integrated circuit it comes into picture once it is being physically manufactured, and also it relates with the layout designing of that circuit, which you are designing. It can be of adder circuit, it can be of counter, it can be of amplifier, or whatever it may be. Any analog processing unit or digital signal processing unit, whichever unit it may be, that backend design mainly it relates with the physical design of that particular circuit, and also it relates with the layout design. It mainly relates with the physical design. It relates with physical design and layout design. Layout design. So now here, when talking about physical design and layout designing, we should even talk about three main parts of this manufacturing and integrated circuit, where how the particular components have been monitored on the integrated circuit and how they are being adjusted or placed on integrated circuits. So these areas where the engineers monitors or look after the components, each and every transistor, how it is working and how the signal is moving. So that particular area are being divided into three different types. It is called as, first one is called as a placement. Second one is called as a floor planning. Third one is called as a routing. So CMO. First, I will talk about the floor planning. Here, floor planning is nothing else but if an integrated circuit or a chip is being given to you, or else I can put it like this: if a silicon wafer is given to you, you'll understand what is meant by wafer in the fabrication steps later in the class. So now, if a wafer is being given to you, or a module of that particular integrated circuit is given to you, then the entire module is being divided into sub modules. That division of the sub modules are restricting the areas, area of a chip or area of a wafer to different circuits is called as a floor planning. And then again, coming to the placement. Placement means it is regarding the inner depth arrangement of the components like transistors or logic gates in this floor plan area. Floor planning means if a 1 centimeter die is been given to you or wafer has been given to you, then that 1 centimeter will be divided into some sub modules, and inside each module, if you are trying to place, if you are trying to arrange the transistors or components like logic gates and different modules, sub modules, that is called as a placement. Floor planning is dividing the bigger module into sub modules, and floor placement means you're talking about the components which are to be placed inside the sub modules. So coming to the routing, has a name itself. It tells that it is a wiring system. It is mainly regarding how the wiring has to be done between each and every component. This wiring system is called as a routing, and this entire process happens. I'm writing this one over here with fabrication. Happens with fabrication. We all know fabrication. You might have heard about the fabrication in normal and or usual days, like metal fabrication. Metal fabrication means what? Some raw substance into required structure. So in the same way here, IC fabrication means will be it's a process of manufacturing the integrated circuits. Fabrication means it's a process of manufacturing and integrated circuits, and this fabrication is very costly process, and it's also complex nature. So now talking about this VHDL, I have told about VHDL. The full form of VHDL is, here V stands for very high speed integrated circuit. Here V stands for very high speed integrated circuit, whereas HDL stands for hardware description language. V stands for very high speed integrated circuit, and HDL stands for hardware description language. So these are the different types of VLSI design. based upon their signals and also based upon their manufacturing. Okay, I will move on to the next concept. The next part is Mosfet. This Mosfet is a main core component for manufacturing any of integrated circuit. Mosfet is mainly core component for manufacturing any of the integrated circuit. So here Mosfet means it's metal oxide. It is metal oxide semiconductor. Metal oxide semiconductor field effect transistor. Field effect transistor. MOSFET means metal oxide field effect transistor. Since we'll be using insulated gates and while manufacturing the MOSFET, this MOSFET is also called as insulated gate field effect transistor. It's also called as insulated gate field effect transistor. IG effect. The short form is IG effect. So MOSFET means it's a metal oxide semiconductor field effect transistor. The other name for the MOSFET is insulated gate field effect transistor. Why we call it as insulated gate? Because while manufacturing or while doing the fabrication process of a gate terminal, we'll be using the insulated oxides. Oxides will be there below the gate terminal. That's why it's called an insulated gate field effect transistor. Insulated gate field effect transistor. Now coming to the types of MOSFET, depending upon the impurities or depending upon the charges, these MOSFETs are basically divided into two main types. The first one is called as N-channel MOSFET. First one is called as N-channel MOSFET. It is also called as N-MOSFET. Depending upon the charge carriers, there's negative charge carriers. The first type of MOSFET is N-channel MOSFET or nMosfet, and the second type of MOSFET is called as P-channel MOSFET. P-channel MOSFET. It is nothing else but pMosfet, or simply we can call it as pMos or nMos, or simply we can even call it as nMos or pMos. So these are the two different types, basically depending upon the charge types, and later they have worked upon both of these two channels, that's N channel and P channel, and they have come up with incorporating both the MOSFETs, nMos and pMos, as one MOSFET, and that is called as a CMOS. That is called as a CMOS. Here, CMOS means complementary. Here, CMOS means complementary metal oxide semiconductor. Complementary metal oxide semiconductor. Metal oxide semiconductor. Then again, see why did they go for CMOS? Because this PMOS and nMOS were consuming more power, which was very less compared to the BJT. But they were in sense of research, that power was very more. So that's why they tried to combine both PMOS and nMOS, and they came up with a kind of MOSFET called a CMOS, and this consumes very less power. Yesterday we have talked about the mode of VLSI. The mode of VLSI is smaller, faster, and low power consumption. The low power consumption of VLSI design is mainly due to this CMOSFET only, mainly due to the CMOS technology only. Then later they have combined the CMOS. Later they have combined the CMOS with the CMOS has been combined with the BJT. The CMOS has been combined with BJT, and they have come up with the fourth kind of MOSFET is called as a bicmos MOSFET. BiCMOS is nothing else but it's a combination of BJT, bipolar junction transistor, and CMOS. So that is called as a BiCMOS MOSFET. Why did they go for BiCMOS MOSFET? We know that up to now we have studied that the CMOS is very good in terms of its low power consumption. But when it comes to the driving part, driving of an output signal at the output part, the driving part is not good as it is with respect to the BJT. So the driving part of the BJT, driving means I'm talking about how an output signal can be easily driven out to get some output or to give some output at the output part of the entire circuit. So that is called the driving nature of a circuit. So the BJT has got very good driving capability, but whereas the CMOS has got lesser driving capability. So they have combined in order to get the benefits of low power and also the driving capability of the circuit. So that's how the BiCMOS technology has come into picture. So depending upon the charge carriers, the MOSFET is divided into N-channel MOSFET, which is nothing else but nMos. It is also called as nMos or nMOSFET. And the second type of MOSFET is called B-channel MOSFET, which is also called as pMosFET or pMos simply. Then again, the third kind of MOSFET is CMOS. By combining N-channel and P-channel, we'll get the third kind of MOSFET is called as CMOS. That is a complementary metal oxide semiconductor. Then the fourth kind of MOSFET, in order to get the benefits of low power and driving capability, they have gone for a combination of this CMOS and BJT. That's how the BiCMOS technology has come into picture. That is nothing else but bipolar junction transistor and also CMOS technology. When these both technologies have been combined, we have come up with a new kind of device that is called BiCMOS devices. So these are the four different types of MOSFETs depending upon the charge carriers. So let us see now the structure or the symbol of nMOS and pMos, and also even this one. What is the CMOS? First one, nMOS. Okay, before entering this structure of nMOS or CMOS, this MOSFET has got three basically. Okay, I'll write it as four different terminals. MOSFET is a four-terminal device. It's a four-terminal device, whereas the BJT is a three-terminal device. We all know that a BJT has got emitter, base, and collector, which are the three terminals of a BJT. But whereas this MOSFET is a four-terminal device, those terminals are: first one, source; second one, gate; and third one, drain. Fourth one is called as a body, or the other name of this terminal is substrate. These are the four different terminals of a MOSFET. So whereas the source is nothing else but it's equal to emitter in the BJT, gate is equal to base terminal in the BJT, and drain terminal is equal to collector terminal in the BJT. So these are the basically three different types of terminals. And along with these three, there's a fourth kind of terminal is there that is called as a body or substrate terminal. So these are the four different terminals of a MOSFET. That's why a MOSFET is called as a four-terminal device. So it's called as a four-terminal device. Now let us see the symbol of nMOS and pMos and also the CMOS. So nMOS, coming to the part of nMOS. nMOS. So see now, these are the four different terminals of a MOSFET. So always remember that for nMOS, drain will be in the upper part, and source will be in the down part, and the source terminal is always connected to ground terminal, that is 0 volts. Source is always connected to, in nMOS it's connected to 0 volts, and gate terminal is a terminal where input signal is being fed into the MOSFET. Gate terminal is a terminal where input signal is fed into the MOSFET, and drain terminal is a terminal where output signal is obtained. Your output is being obtained. So let us see how this nMOSFET will be working. your nMOSFET will turn on only when a high voltage is given to this one. A high voltage is given to this one. Since it's a digital kind of circuit, whenever the input signal is equal to 1, when 1 is taken as a logic 1 is taken as a high voltage. So whenever the logic 1 is given over here, the nMOSFET will turn on, and that's how the signal will move from will move to the output terminal. Will move to the output terminal. So this is the symbol of nMOS. nMOS symbol. nMOS symbol. So now let us see pMOS symbol. I hope it's this particular part is clear to you. The next one is the pMOS symbol. pMOS symbol. The major difference between the pMOS and nMOS is that a bubble will be added at the gate terminal. If it's a pMOS, a bubble will be there. If it's an nMOS, a bubble will not be there. That's how you should, by looking at the structure, you should understand whether it's a pMOS or nMOS. So see now. So if this bubble is there, it is called as a pMOS structure. So this is the gate terminal, and here at the gate terminal, always an input signal is being fed. Input signal is fed, and this is your drain terminal, where your output is obtained. Output is obtained, and this is your source terminal, where it is connected to higher voltage, the supply voltage, VDD. Source is always connected to the VDD, whereas in case of nMOS, the source of nMOS will be connected to ground terminal. In case of pMOS, the source will be connected to VDD. And coming to this one, and always keep in mind, see the body terminal or the substrate terminal, the fourth terminal will be always connected to the source terminal only. The body has to be always connected to source terminal of a particular structure or particular device. If it's an nMOS, the source will be connected to, the substrate will be connected to source, which is in the down, and if it's a pMOS, the substrate will be connected to source, which is in the top. So now here I'll be connecting the substrate. So this is your substrate or body. So these are the 4 different terminals of a MOSFET. The 4 different terminals of MOSFET, pMOSFET are source, substrate, gate, and drain terminal. Drain is a terminal where output is being obtained, and gate is a terminal where your input is fed into the circuit or into the device. Then source is a terminal where the main supply is being given to that particular device. So always, in order to recognize or in order to classify nMOS and pMOS symbolically, then this bubble is very important one. The bubble differs pMOS and nMOS. If the bubble is being connected at a gate terminal, it is called as a pMOS device. If the bubble is not connected, we call it as an nMOS device. And I hope the structure is clear to you, and I'll move on to the next part. That's the CMOS. CMOS symbol. As I told you that CMOS is nothing else but it's a combination of pMOS and nMOS. As I told you that CMOS is a combination of pMOS and nMOS. So I'll connect the pMOS and CMOS one after the another, so that the entire structure of CMOS will be obtained. This is your source, I'm denoting by S, and this is your body or substrate, and then here, see now. This part is the drain of a pMOS, and this is the drain of nMOS. This is the drain of nMOS, and this is your gate terminal of pMOS, and gate terminal of nMOS, and this is your substrate of substrate or body of the nMOS. As I told you that the body of a pMOS has to be connected to the source, that is in the top part, and whereas the body of nMOS has to be connected to the source of the nMOS, that is in the bottom part. It means indirectly you are connecting the body of pMOS to the high voltage, to the main supply, and the body of nMOS is connected to the ground terminal, which is nothing else equal to 0 voltage. So now I need to get a combined output of these two circuits. That's the actual meaning of CMOS. CMOS means it's a combination of both pMos and nMos. So for that one, they'll connect this drain, both the drains have to be connected, and this is a place where your output has been obtained. So this is a place where your voltage output, V out means voltage output, which is fed out. And then here, I need to give a combined input to this one. I need to give a combined input to this one. So when I give a combined input here, so this becomes, I need to short this over the gate terminals, and this becomes my input signal, which I can write it as V in. Input voltage will be fed into this CMOS here. So now, how does this pMos and nMos will be working? As I told in the previous topic, pMos. For the pMos, whenever you give 0 volts, whenever a 0 volt is being given, whenever a 0 volt is fed into the pMos will turn on. pMos will turn on and nMos will turn off. And nMos will be turning on only when input voltage is 1. Means it's like if 0 volt is being given. See, I'm giving only one kind of voltage here. I can give either 0 volts at a time or else 1 volt at a time. When I give 0 volt at a time, both these devices will be fed with the same 0 volts. So 0 volts means when an input signal is equal to logic low or logic 0, so at that time the pMos will be turning on and nMos will be turning off. So that's the working condition of first state of the CMOS. Then whenever I give input signal is equal to 1, in this case pMos will be turned off, nMos will be turned on. Whenever logic 1, it is nMos is going to turn on, the other one is going to turn off. If it is logic 0, pMos will be turned on and nMos will be turned off. So this is a working condition of CMOS. I'm writing here. For logic 1, for logic 0, pMos on and nMos is off. Means your device will not be working. nMos off means device will not be working. Now, for logic 1, whenever your input is logic 1, then what happens? Your pMos is off, nMos is on. nMos is on. So this is how a CMOS device will be working. So this is a symbol of the CMOS structure, where it has got 4 terminals of pMos and also 4 different terminals of nMos. So this is regarding the CMOS structure. I hope the particular topic is clear to you all, and I can address this one. Now, depending upon the manufacturing part, I'm not going into the much detail about the next concept. Why? Because in detail we'll study in the next coming classes. So depending upon the manufacturing methods, VGS means the voltage which is given between the source and drain terminal and channel. Channel is nothing else but it's like a bridge between
Excuse me, sir.
source and the drain.
Sir, excuse me.
Excuse me.
Sir, what is the symbol for bicmos, sir?
See, bicmos means the entire input part will be CMOS structure, output part will be only BJT. One BJT will be connected.
Okay, sir.
That's why I am not given. It's simple like here. It will be like the input, see, because I can't go on drawing the entire models of all the inputs, because the input part will be different circuits will be there. Like amplifiers will be there, counters will be there, signal processing units will be there, many application oriented circuits will be there. All those application oriented circuits will be designed with the help of CMOS structure, and that will be given where that output of this structure will be given as an input to the BJT. One BJT will be connected. That's the BJT. BJT will be connected to the output, and that will get out the output of the entire circuit.
Okay, sir. Thank you, sir.
Yeah, both will be anyhow it is connected to the voltage power supply.
Okay, sir.
Okay, this will be a simple structure of bicmos. This one
Okay,
is
sir. Thank you.
a simple structure of bicmos. Okay, fine. And here input signal will be given to the input part of the CMOS. That the CMOS structure is used to design the input part, and this input part will give some output that acts as an input to the BJT, and the BJT will fed out the entire output of this entire structure. So this is the simple symbolic representation of bicmos. Okay, is it clear now?
Yes, sir.
I hope my voice is clear now.
Yes, sir.
So, depending upon the manufacturing methods, VGS means the voltage which is being connected between the gate terminal and the source terminal. So that's a VGS, and depending upon the channel. Coming to the channel is a bridge between the source and drain terminal where your charges will be moving along this channel. If the charges are moving, then I can say the channel is conducting. If the charges are not moving along this bridge, I can say the channel is non-conducting channel. So depending upon these factors, the MOSFET is divided into, MOSFET is classified as MOSFET is classified as first one, enhancement mode MOSFET. The second one is called as a depletion mode MOSFET. Enhancement mode MOSFET and depletion mode MOSFET. Now coming to what is meant by enhancement mode. In the enhancement mode, when VGS is equal to 0, in the enhancement mode, if VGS is equal to 0, your MOSFET will be completely, it will be in an off state. MOSFET will not be working. If VGS equal to 0, then MOSFET is off. MOSFET is off. That's why it is called as a normally open switch. It acts as an open switch. Enhancement mode MOSFETs will act as an open switch. So whenever the VGS, whenever the voltage between gate and source terminal is equal to 0, then this particular MOSFET will be in the turned off situation. Why? Because the reason why it is in the off state, because if VGS is not being fed, if the VGS is not being given or it is not triggered, then a channel will not be developed. First of all, there is no channel. If there is no channel, what happens? There is no point of talking about the movement of the charge particles from source to drain. If the charge particles are not going, definitely the channel is off and the entire device goes off. So that's why, since there is no channel, whenever the VGS is equal to 0, the channel will not be produced. Since there is no channel, the MOSFET will be in off state. Coming to this depletion mode MOSFET. In depletion mode MOSFET, if VGS equal to 0, volts, I mean 0 volts in it. If it is 0 means it is at 0 volts, VGS equal to 0 volts, even though the VGS equal to 0, there exists some channel, there will be a channel existing. Because of that one, the channel will be always in the on state. Even if the VGS equal to 0 in the depletion mode MOSFETs, a channel will be present. Because the channel is present, the movement of charge particles takes place between the source and drain terminals. So that's why the entire device will be in the on state. Channel is present. Therefore, it is in the on state. Since it is in the on state, I can call it as a closed switch. Depletion mode MOSFETs are called as a closed switch, and this enhancement mode MOSFETs are called as a normally open switch. Enhancement mode MOSFETs are called as an open switch, whereas the depletion mode MOSFETs are called as a closed switch. Why it is closed switch? Because a channel is present between the source and drain. The path between this source and drain is closed. It means there exists some kind of path. Since because of this path, the charge particles can easily move from source terminal to drain terminal. Since there is a channel movement or the charge particles movement through the channel, the entire device will be in the on state. Since it's an on state, the on state will be happening only whenever you close the switch. If the switch is closed, then only the charge particles will be moving. So these are two different types of MOSFETs depending upon VGS and channel. So let us see how the symbols of this enhancement mode and depletion mode. See, I'm drawing over here. If it's an enhancement mode, enhancement mode MOSFET are similar to one of the structures I have drawn in the previous case. same nMos and pMos structures. But coming to this one, I'll draw only the depletion mode symbols. This is the drain. This is a source, ground terminal. This part is ground terminal, and this is a gate terminal. And we will be having anyway source is connected, so the substrate is connected over here. This is a body. Can you tell me what kind of Mosfet is it? Can anyone tell me what kind of Mosfet?
N channel.
N channel. Good. It's an N channel depletion mode Mosfet. It's an N channel depletion mode Mosfet. Then coming to the next part. This will be the Mosfet where VDD is connected over here, and this will be your drain terminal. Since it's VDD is connected, body will be connected to this one body, and this is gate terminal. So this is a channel depletion mode Mosfet. So these are the two different types of Mosfets depending upon regions and also the channel. Okay. The concept is clear. Shall I erase it?
1 minute, sir.
Okay, we'll move on to the next concepts.
Okay, sir.
Is it completed now? Have completed
Yes,
this now?
Yes, sir.
Okay. I'll try to give the summary of whatever we have studied, because it's already time up now. Because the next concept will be, I thought of discussing about the fabrication steps. Like there are three different kinds of fabrication. There's nMos fabrication, pMos fabrication, CMOS fabrication, and later, if possible, only with respect to few steps, we'll study about the CMOS fabrication also. But basically, as per your university paper is concerned, nMos and pMos, and also one type of CMOS fabrication is very important. So we'll mainly focus upon nMos, pMos, and CMOS fabrications. So in the next class, we'll study about what is meant by CMOS fabrication, what are the steps involved in the CMOS fabrication. So in this particular class, we have discussed about what is meant by VLSI and how the VLSI has been classified into different types depending upon signals. Depending upon signals, we have seen that VLSI has been classified into three different types. There is analog VLSI design, digital VLSI design, and the third one was pixel signal VLSI design. And depending upon the designing part or the testing part, or else depending upon the manufacturing part of the device, the VLSI is again divided into two different types. First one is called as a back-end VLSI, and second one is called as a front-end VLSI. If you talk about the front-end VLSI, the front-end VLSI design is mainly related with the designing and testing of the integrated circuit. Means here in the front-end VLSI design, mostly they'll be working with the coding part or the scripting part. And as for VLSI is concerned, there are basically three different types of coding. And again, testing, for the testing, they'll be using the RTL1, RTL level coding. So the first one kind of VLSI programming language is vhdl. vhdl is nothing else but very high speed integrated circuit hardware description language. And second one is a verilog, and third one is called as a system verilog. And fourth one is for testing, we will be using a RTL level coding. And coming to the backend VLSI design, this is mainly concerned with or related with the physical design and layout designing. So here in physical design and layout designing, basically every engineer will be thinking about how a particular wafer or the integrated circuit has to be modeled, or how it has to be efficiently used, such that each and every components have been fixed in one smaller area. You might be knowing that now the size of integrated circuit is only in something like a millimeter cross millimeter only. A chip size is of millimeter cross millimeter. So you can imagine how complex is the area where the physical designing or layout designing has to be done. So that's why again it has paved the path for different kinds of engineers in VLSI, called as a placement engineers, routing engineers, and floor planning engineers. where the floor planning engineers will be mainly dealing with the concepts like how the entire circuit or the entire wafer has to be subdivided into submodules, and then the placement engineers will be designing these submodules will be given to different placement engineers. The placement engineers will be mainly concentrating the area where how each and every component, different logics has to be placed efficiently in a smaller area. That's regarding the placement engineers and floor planning. Once they, all the modules are brought together, the routing engineers will think about connecting the interconnections or connecting the wiring. All this wiring and interconnections will be done by the routing engineers. Why? Because wiring is very important. If any small mistake or any kind of error takes place, the signal cannot move from that particular point to the next level of the circuit. So routing is very important part of this VLSI design. So later, after seeing about that particular topic, we have gone into metal oxide semiconductor. That's nothing else but Mosfet. Mosfet is basically divided into four different types. The first one is N-Mosfet, second one is P-Mosfet, and third one is C-Mosfet. And after that combination of CMOS and nMos, it has come the fourth kind of MOSFET, that's a bicmos MOSFET. And we have even seen the symbols of pMos, nMos, and CMOS, and different even the structure of bicmos MOSFET. And depending upon the channel and VGS, your MOSFET is divided into two different types again: enhancement mode MOSFET and the depletion mode MOSFET. In the enhancement mode MOSFET, if VGS equal to 0, the channel will not be present. So that's why it is called as an open switch. Channel is nothing else but it's a bridge or a path between or an area between the source and drain. And the second kind of MOSFET is called depletion mode MOSFET. If VGS is equal to 0 volts, then even though the VGS is equal to 0 volts, the channel will be present, and that channel will try to keep the MOSFET in on state. That is the working state. That's why it's called closed switch. Then how to overcome this depletion? Since because if the device is continuously on, then definitely at one particular point there is a chance of I can tell that degrading of the device. The device might go into off state or it might not work. So in order to overcome this kind of situation, we need to again supply negative voltage to this one. If the negative voltage is been given, then the depletion mode MOSFET, the channel can